Imagine if the most destructive force in the universe could teach us how to build better computers. That's exactly what's happening right now, as scientists are using theories about black holes to revolutionize how we store and process data. Welcome to the fascinating world where cosmic monsters meet cutting-edge technology. Black holes have captivated scientists for decades, but there's one puzzle that kept physicists awake at night for over 40 years. It's called the black hole information paradox, and solving it might just transform our digital future. Here's the mind-bending problem. When something falls into a black hole, it seems to disappear completely from the universe. But according to quantum mechanics, information can never be truly destroyed. So where does it go? Stephen Hawking first identified this paradox in the 1970s when he discovered that black holes aren't completely black. They emit radiation, now called Hawking radiation, and eventually evaporate entirely. If a black hole evaporates and takes all its information with it, that breaks fundamental laws of physics. It's like burning a book and expecting to reconstruct every word from the ashes. Impossible, right? For decades, physicists battled over this problem. Some argued information was lost forever. Others insisted it must be preserved somehow. The debate grew so heated that Hawking made a famous bet with fellow physicist John Preskill about whether information could escape black holes. Eventually, Hawking conceded, acknowledging that information probably does survive, encoded in ways we're only beginning to understand. Here's where things get really interesting for computer science. The solution to this paradox suggests that black holes store information in the most efficient way physically possible. They encode data on their surface, their event horizon, rather than throughout their volume. Think of it like this. A sphere's surface area grows with the square of its radius, but its volume grows with the cube. Black holes maximize storage by using surface encoding, a principle called the holographic principle. This discovery has profound implications. It suggests that three-dimensional space might actually be a projection of information encoded on a two-dimensional surface. Your entire reality could be a hologram. But beyond the philosophical implications, this principle is inspiring revolutionary approaches to data storage and processing. Traditional data centers store information in three-dimensional arrays of hard drives and servers. They're massive facilities consuming enormous amounts of energy. A typical large data center uses enough electricity to power 50,000 homes. They generate so much heat that cooling systems account for nearly 40% of their total energy consumption. This approach is hitting physical limits as we generate more data than ever before. Enter the concept of dark star data centers, named after the theoretical precursors to black holes. Engineers are applying black hole information theory to create fundamentally more efficient storage systems. These designs use principles from holographic encoding to maximize data density while minimizing energy consumption. Instead of storing data throughout a volume, these systems encode information on surfaces using quantum properties of materials. One breakthrough involves using two-dimensional materials like graphene. This carbon sheet is just one atom thick, but incredibly strong and conductive. By encoding data on graphene surfaces using quantum states, researchers can achieve storage densities approaching theoretical limits suggested by black hole physics. A single sheet could theoretically store more information than thousands of traditional hard drives. The connection goes deeper than just surface storage. Black hole thermodynamics, which describes how black holes process information, has inspired new approaches to managing heat in computing systems. Black holes are the most efficient heat engines in the universe. They convert matter to energy with perfect efficiency according to Einstein's famous equation. Data centers are essentially heat engines running in reverse, and black hole physics offers blueprints for optimization. Researchers at institutions like MIT and Stanford are developing cooling systems inspired by Hawking radiation. These systems allow heat to escape from computational surfaces in controlled ways, mimicking how black holes release energy. Early prototypes show potential for reducing cooling energy requirements by up to 60%. That's not just cost savings, it's essential for sustainable computing as global data demands skyrocket. Another application involves error correction, one of computing's biggest challenges. Quantum computers, which promise revolutionary processing power, are extremely sensitive to errors. Information encoded in quantum states degrades rapidly through a process called decoherence. Black hole information theory suggests robust encoding schemes that protect information even in extreme conditions. Physicists studying how information escapes black holes discovered that it must be encoded redundantly across multiple quantum states. This insight led to new quantum error correction codes that are more efficient than previous designs. These codes allow quantum computers to maintain information integrity longer, bringing practical quantum computing closer to reality. Companies like IBM and Google are implementing these black hole-inspired codes in their quantum processors. The holographic principle is also inspiring new architectures for artificial intelligence systems. Neural networks, which power modern AI, typically operate with layer upon layer of interconnected nodes. But holographic encoding suggests that complex computations might be performed more efficiently using two-dimensional networks with specially structured connections. Research teams are building experimental AI chips using this approach, showing promising improvements in both speed and energy efficiency. Here's a fun fact that shows how far we've come. The total amount of information humanity has created throughout all of history would form a black hole about the size of a large building if compressed to maximum density. But we're generating so much new data that this hypothetical black hole doubles in size every 2 years. Without revolutionary storage approaches inspired by actual black holes, we'll soon run out of physical space and energy to store our digital universe. Major technology companies are investing heavily in these dark star data center concepts. Microsoft has announced plans for a prototype facility using holographic storage principles. Amazon is exploring black hole-inspired cooling systems for their cloud infrastructure. These aren't distant dreams. They're active engineering projects that could reshape computing infrastructure within the next decade. The implications extend beyond just better computers. Medical imaging devices using holographic encoding principles can store and process diagnostic data more efficiently. Climate modeling systems, which require enormous computational resources, could run on black hole-inspired architectures that dramatically reduce energy consumption. Even your smartphone might one day use storage systems designed according to principles learned from the universe's most extreme objects. What makes this story so remarkable is how pure theoretical physics, driven by curiosity about the universe's most exotic phenomena, leads to practical technologies that improve daily life. When Hawking and his colleagues debated information paradoxes in the 1970s, nobody imagined their work would inspire the next generation of data centers. This is science at its best, following questions wherever they lead. As we generate more data, stream more videos, and build more AI systems, the physics of black holes might be what saves us from drowning in our own information. The universe's ultimate information processors are teaching us how to build better ones here on Earth. So next time you upload a photo or stream a movie, remember that cosmic monsters billions of light years away helped make it possible. What other secrets might black holes hold that could transform our technological future?